Hi folks, we're going to take a look at how we can use transformations to sketch the graphs of some polynomial functions. Now I'll say right off the bat that this is not the method we're going to use most often, but does allow us to review the concept of transformations. So what I'm going to graph here is y equals negative 2x plus 4 cubed plus 1. Okay, now to use transformations, we have to compare this function to a simpler, what we call a parent function. So you look here and you realize that you've got some expression that is being cubed, and then we're multiplying and adding numbers to that. So it makes sense to use y equals x cubed as our parent function. Okay, so we're going to compare this function here to the parent function y equals x cubed. Okay, and the first thing we have to do is identify what transformations we're working with. Now keep in mind that in order to correctly identify transformations, in particular the horizontal ones, the function has to be in a particular form. So let's look at the general form of a transformed function. So if y equals f at x is our parent function, y equals a times f at b times x minus h, okay, plus k. Okay, this represents a general transformation of the parent function f at x. So first of all, don't worry if the letters you used last year might have been different. It really depends on which textbook you're using. But what's important to notice here is that the input to the function has to be in factored form in order for you to correctly identify those horizontal transformations. So that's going to be my first step here. Okay, so this input of 2x plus 4, I'm going to rewrite as 2 times x plus 2. Okay, so now I can see that I've got a reflection in the x-axis. Okay, I've got a horizontal. Now here you have to be careful. Anything that's horizontal will always be opposite. So here it's a horizontal compression by a factor of a half. So we're going to be multiplying our x values by half. Then here we have horizontal translations 2 units to the left. Again, always opposite to what you see. And then here we have a translation up by 1 unit. Now, if you notice the order in which I gave those transformations, I'm following essentially bedmass. I have to first consider the multiplicative transformations, so things like reflections and stretches, and then the additive ones, which are the translations. Okay, now there's a few ways you can go about doing this. The method I'm going to use is to do a point-by-point transformation. So I'm going to transform a few points from x cubed to points on this graph here, and then use those to sketch the graph. Now again, because we're not going to be using transformations too much, I'm just going to use 3 points on my parent function. Okay. Now just so that we see something different, I'll use function notation here. So okay, so I'm going to call x cubed my f at x. Okay, and I'm going to take 3 points. So let's remember what x cubed looks like. Okay, so it has this shape here. So we know that our transformed function will also have the same general shape. Okay, things might be stretched or things might be reflected or translated, but the general shape will be the same. So I'm going to use sort of 0, 0, I think a pretty obvious point to use here. And I'm going to make sure to take points on either side so that it gives me a sense of the shape. So I'm going to pick 1, 1. Okay, and I'm going to pick negative 1, negative 1. Okay. Now, if I wanted more precision, I could definitely pick more points, but I'm just going to stick with these 3. Okay, and what I want to graph now is the function negative f at 2 times x plus 2 plus 1. Okay, so there's this just another way of writing this function. I call this explicit form, and this is using function notation. Okay, so let's see how these are being transformed. Okay, so remember what we said. We have to do the multiplicative ones first. So let's see what happens to the x components. Okay, so here, remember always the opposite for horizontal. So here I have to, instead of multiply my x components by 2, I divide them by 2. So I'm going to do 1/2 times my x component of 0. Okay, and then here instead of adding 2, do the opposite, subtract 2. Okay, for the y values, I take the negative of my y value. Okay, and then I add 1. Okay, so the final point, well, is 0 minus 2, negative 2. 0 plus 1 is just 1. Okay, so the point 0, 0 gets transformed to the point negative 2, 1. Okay, and now I just do the same thing for the other one. So 1/2 times the x value, okay, minus 2, and then negative the y value, which happens to also be 1, plus 1. Okay, so here we have 1/2 minus 2, so that's negative 3/2. Okay, and negative 1 plus 1, 0. Okay, same thing, 1/2 times x value of negative 1 minus 2, and then negative the y value, which is also negative 1, plus 1. Okay, so this point becomes negative 1/2 minus 2, so negative 5 over 2, and here 1 plus 1, 2. Okay, and now that I have these points, I can sketch the graph of the function. Okay, so let's get a piece of graph paper here. Okay, now make sure you're labeling your graph. Okay, in particular, I want to see scales on both the x and the y. So I look at my x components and negative 2, negative 3/2, negative 5/2. So I'm all on the left side. Now, on a test, I'd probably not give you any axes, okay? Because it looks like it makes more sense to put our y-axis a little more to the right, okay? But here, I think I'll go up by 1 unit. So 1, 2, okay? And if we look at the y values, they're all pretty small, so I'll go up by 1 unit also, okay? But if it made more sense to change these scales, I would do that. So now I just have to plot my points. So let's start with that middle point, negative 2, 1. So negative 2, 1. Okay. Now we have negative 3/2, 0. So negative 3/2, 0 here. Okay. And now we've got negative 5/2, negative 2.5, 2. Okay. Now with these points, now you have to be careful because you have to keep the shape of the graph. Okay, so since I had a reflection in the x-axis, instead of going from positive infinity to from negative infinity to positive infinity, I'm going to be going the other way around because I had this reflection. Okay, and because of this horizontal compression, it makes sense that my graph should be a little skinnier. Okay, so I'm going to do my best here to draw. Okay. So, and again, I have to really try to keep that shape going. Okay. And there's my graph. Okay. Again, we don't expect perfection here, but not surprisingly, the graph is a little skinnier because of that horizontal compression. Okay. The end behaviors have changed, okay, because of that reflection in the x-axis, and of course my translations 2 to the left and 1 up. Okay, now notice here, had you not factored your input, you would have had a translation 4 units to the left. You would have had the wrong answer. Okay, so I'm not going to give you many of these, but just give you a couple to work on these transformations, and make sure you're always checking your answer with Desmos. Okay, that's it for now.